one more comment about Euler circuits. One way that Euler circuits can be used in an application is consider things like a route involving city streets and trying to complete a route that means traveling a certain grid of streets and returning to the start and retracing streets as little as possible. So in this context here, you have a graph, and what we're going to do is do what's called Eulerization. And by that I mean we're going to add edges in such a way that the result will have an Euler circuit. But if this is to correspond to somebody actually traveling the streets, the only edges that we can add will be those that reproduce a edge that is already there, a street that's already there. So repeating existing edges. So we'll make multiple edges that repeat existing edges in order to create an Euler circuit. So in certain contexts, like a rectangular street grid, as I put down here, there is an algorithm that will produce an optimal solution. And the idea is that you've got to somehow get even vertices where you have an odd vertex. So for example, this one right here that I'll create as a blue dot is an odd vertex, and in fact all the ones on the edge or on the outside border are odd except the four corners. The four corners here are even, they're just 2's, but everything else is a 3. On the inside we have only 4's, so there's no issue with that. So the algorithm would be to start somewhere where on the outer edge. A good location would be to start at a corner and then proceed in either the clockwise or counterclockwise direction, clockwise or counterclockwise, around the outside. And each time you hit a vertex that is odd, add an edge to the adjacent one, one edge to adjacent one, and proceed in that fashion from that point on. So if you add that edge there, the next edge would be from this one that we just visited. That's now a 4. So we'll go to the next one. That's odd. So we'll add one from that to the next one, not even considering what the next one is in terms of odd or even. But that turns out that these are both even now. So we'll continue around. No problem here. This one's odd, so we'll add an edge just to the very next one, so it duplicates that one block, in other words. And then we'll continue down here. This one's odd, so we'll add an edge here. Now unfortunately that turns that one into an odd. Now that's odd. So we'll add one to that, from that one to the next one. That was okay because that one made that even. And then it'd be this one odd goes to this next one. And then down here we're going to run into the same trouble we did at the previous corner. We're going from an odd one, adding an edge to make it even, but it turns this one to odd, so we have to add that one there. And then there's one more that we add. So that's an Eulerization. And that tells us how many streets we have to duplicate in the optimal way so as to complete the route. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 duplicates or repeats. Let's call it repeats. Okay. Now there's fancier things we can do with this, and I did one in class like that, I think, where you could have a grid that looks like we had up there, but maybe there's some blocks that don't have any streets in them. So for example, we might have the grid that looks kind of like this. Maybe it's a grid looks like this, except that maybe this block right here is missing. So what I have is something like that. And who knows, maybe that one's missing there, so maybe I have something like this even. And let me just draw another one in there to make it a little richer. And so, you know, you can't cross that because that's not street, it's fenced off or whatever. It's got, you know, dangerous equipment on it, or all kinds of things could be true, but you're not going to be able to cross that if you're somebody walking a route. You're definitely not going to try to cross that. And then on this in this case, you know, the border we can do in a similar fashion as we did before, but then you have to figure out what are you going to do with this one and make some sort of an Eulerization for that one right there. So where are the issues? Well, that's a 2, that's not a problem, but that's a 3, and that's a 3 there. So one of the efficient ways to do this, in this case, that's a 1, 2, 3, 4, so everything else is a 4. So we'd probably add those edges there to make it most efficient. And then on the outside do the same sort of Eulerization we did before. So we do this here, and then this here, and this here, and then this here, and then this here. Oh, I did it nicely so that we don't have to do any of those wraparounds in this case here. Right, so there'd be an Eulerization. So the next thing we want to turn to is the idea of a Hamilton cycle. So before we were looking at circuits that didn't repeat edges but may have repeated vertices. A Hamilton cycle is a cycle in a graph that visits every vertex and returns to the start. Well, a cycle does that anyway, right? A cycle is a closed walk that repeats no edges. So it's often called a Hamilton circuit as well. So let me sketch one in this first case here, and maybe you could pause and do it yourself, see if you can get one in this grid graph on the left. Can you see a Hamilton cycle for that? Well, there's actually a lot of them that you might think about, but the one I'll draw will start here and goes along here, comes in, comes out, goes in, goes out, goes around like that. That meets every vertex. It doesn't consume every edge. That's not the issue. You just want to visit the vertices. And in fact, the idea behind this is maybe something like you want to visit a number of cities in order to complete tasks that you need to do for your job. And so you'd like to be able to do it by just visiting each city once and returning home. That relates to what's called the traveling salesperson problem that I'll mention briefly on the end of this particular clip. Before we get there, let's think of this other one here and see whether there's a Hamilton circuit for that, Hamilton cycle. The issue with this one right here is that, well, you have to do everything on the outside, all the vertices on the outside here somehow, and then you have to do all the ones on the inside, and everything is either an outside one on the inside rectangle, one or the other. So, but you have to get from one to the other at some point. So, you know, more or less arbitrarily, let's just say, okay, I'm going to go, this is the way I'm going to go from the outside to the inside, or vice versa. And since it's going to be a cycle, if we do get one, it doesn't matter which way we think about walking the cycle. So I'm going to think about going in that way. I'm going to say, okay, we're going to go in like that and see what happens in that case right there. It may be helpful to have labels on the vertices. A, B, this is B here. C, D, E, F, G, H. Let's go in. I, J, K, L, M, N, O. Okay? So if we start at B and we're going to try to end up at B, then we have to go either to the right to K or to the left to J. Now it doesn't matter which because of the symmetry of this graph right here. So let's suppose we go to K over here, like so. And then the question is, could we possibly exit by going down to L and then out to A and then out to D and do whatever we need on the outside for a while? The problem there is if we go out to D, as I've kind of tried to indicate with the highlighting there, then we either go up to C and we're stuck, we can go nowhere else, or we go down and there's no way for us to visit C after we've gone down. There's no way to get back to C. So that would not use every vertex, which is what a Hamilton cycle has to do. So we can't go out there. So we continue on, come down to M. Can we go out at N and to F? The same problem would result because if we go out here, whoops, let me get that shading again. If we go out here, then we can either go to the right or to the left. But whichever way we go, can't go to the other direction ever, because if we go to the right, there's no way of getting back over to the left. So there's no way to go out there. So we must continue on and come over here. But now we have to go out, because if we don't, we're stuck. So if we go out here, then we have the same problem that results. Either we go up to A and we'll never be able to get to G, E, D, and C, or we go down to G and we'll never be able to get back to A. This has no Hamilton cycle. It's a little harder to prove whether or not something has a Hamilton cycle because there is no efficient algorithm for finding a circle, for determining whether a circuit exists. No simple criterion, as in the case of the Euler circuit. So, conditions for Hamilton cycles, well, these are some for when there aren't Hamilton cycles, and we're really just touching on this at a very elementary level, not getting into all that is known about this. It is pretty clear that if there is a bridge, there is no possible Hamilton cycle, because if we once we cross that bridge, there's no going back to complete a cycle. The same thing with the cut vertex. Once we cross that vertex, say like so, there is no getting back to get back to the start there. And this could not be the start and end because we'd have to cross it twice. So a cut vertex prevents a Hamilton cycle. There are a couple of theorems that tell us in certain cases when there is a Hamilton cycle. These were discovered in the 1950s and 1960s. Dirac's theorem, but let me back up and just say both of them say something like if the degree at each vertex is large enough, or if there are enough edges, you're going to be able to find a Hamilton cycle that goes through every vertex and returns to the start. And one is you have a simple graph of order n greater than or equal to 3, in which each vertex has a degree which is greater than or equal to half the order of the graph, half the number of vertices. Ory's theorem is similar, except in this case you only need to know that for disjoint or distinct vertices, the sum of the degrees is always at least the order of the graph. So if there's enough edges, like I said, in a simple graph, these are both simple graphs in the hypothesis, then you'll be able to get a Hamilton cycle. I'm not going to say anything more about those. I will say something about some of the places where this occurs. And the first one I've referenced already, the traveling salesperson problem. You might have cities that you have to visit, and you want to do this in an efficient way, and there's a cost associated with each edge or each trip from one city to another. So you have cost associated with each of these, and you want to know how to choose the route of least cost. So you'd have a cost associated with each edge, and a way to envision this is you might have a KN graph with n being the number of cities, and the edges are weighted with a cost, labeled with a cost. And the question is, how do you find the Hamilton circuit among the very many that are there in a complete graph that would give you the smallest total cost, adding the weights on the edges that you would use for your journey? Well, in a KN, if you have one of the vertices is a start, so there are n-1s that remain, n-1 cities that remain that you have to visit and then return to the start, then for your first leg there's n-1 cities to choose from, and there's an edge to each one of them, and then there's n-2 that you still have to visit from that one, and so on down the line down to one edge that you would take to get back to your original city. So there's n-1 factorial different Hamilton circuits in a KN graph with a specific start. Actually, the specific start is not such a big deal, because any cycle you could view as any one of the cities as being the start in n vertex, right? Because it has to go through every vertex. Now, the cost is going to be the same no matter which direction you take that cycle. So in fact, you only need to look at n minus 1 factorial over 2 cycles to check. So you might say, well, just list them all and check them all. Yeah, just find out how many are there. Just add them all up, put them in your computer, bing. Well, if n is 25, then if each addition takes a nanosecond, say, then the number of additions that we have to do up here, there's n additions for each cycle, so it'd be n times n minus 1 factorial over 2, which unfortunately is quite large. It's in the neighborhood of 245 million years. So not likely that you're going to be able to use that method. Very interesting to see about how large that can be, which is 25 cities. So that would be what we call the brute force solution, just trying to check every possibility. Not likely that we're going to try to do that. There are approximate algorithms that, with a high probability, give an answer that is very, very close to the optimal solution. And so in the real world, that's the kind of thing we would have to do. Those algorithms would produce a reasonable answer in a reasonable amount of time, and as I say, with high probability would be very close to the optimal solution. So that's what one has to do in that kind of a case. All right, well, we're going to turn next time to planar graphs, but let's stop here on the Hamilton circuits and cycles.